In the previous videos in this series, we discussed different types of noise, and we also discussed specifications for a specific noise generator to meet our purposes, that is, electronic music. And we also discussed where we get our original random noise signal to work with. In this video, we will actually look at the design of a white noise generator, and then in subsequent videos we will take that white noise signal and modify it into other types of noise. First, we will use the reverse biased semiconductor junction as we discussed previously. The resistor that you use from the emitter to the positive supply is not particularly critical, but in general, with most transistors, you will probably want that to be in the range of 100K to 1 meg. There are some issues that crop up if you make it a lot bigger or a lot smaller than that. So I have chosen 330K. Since the raw noise signal at the emitter of the transistor is very small, on the order of a few millivolts, we're going to have to amplify the heck out of that thing in order to get it up to our standard 5-volt signal levels. The problem is that there is a large DC offset of several volts, and if we just run that straight into our amplifiers to get the needed gain, it's going to peg the op amps to the power supply limits, and we're dead in the water. Since we need to get rid of the DC offset, we just need a simple little high-pass filter. Now, as far as the cutoff of this filter goes, we certainly want it to be below the audio range, so less than about 16 hertz, but we don't want it to be too high because we plan to use the white noise signal and put some very serious low-pass filtering on it to generate a slowly moving sub-audio random signal. So we need to retain the sub-audio components, at least within reason. The problem with making the cutoff frequency very small is that in order to keep the resistor to a reasonable value, say in the low megohm range, we would have to put in a really huge capacitor. Now, I mean huge in terms of physical size as well as capacitance, and they also get expensive. So I have chosen two components, 1 meg and 1 microfarad for this. You can get a multi-layer ceramic capacitor in 1 microfarad that's fairly inexpensive, and it's also very small. This gives us a corner frequency of about 1/6 of a hertz, so that should be sufficient. Now that we've gotten rid of the DC offset, the noise signal at the non-inverting input of our amplifier is going to be a few millivolts. Now, since we need a 5-volt signal, that means we're going to need a gain of probably over 1,000. Now, if we look at the gain bandwidth product for the TL07 series, which is what we will be using here, it's 3 megahertz. So that means that if we divide 3 megahertz by the maximum frequency we want to come out of that thing unchanged, which is the upper end of the audio spectrum, which is 20,000 hertz, 3 meg divided by 20K is 150 maximum gain. Oops, that's not enough. So we're going to need 2 stages of amplification here. I will simply set the first stage gain to 101. That doesn't push our limit of 150 too much, and that means that our next stage is going to need a gain of maybe up to about 50. Now, we will have to make one of these gain stages variable because the individual transistors are going to vary in how much noise they generate. So I'm going to set the second stage up to have a gain between 5 and 50, which would give us an overall gain of 5,000. I have found that with modern 2N3904s, which seem to be very, very uniform in the amount of noise they generate, that this is sufficient range to get our 5-volt signal. let's go back for a moment and look at that first stage. Now, if we look at the specs for the 07 series of op amps, we see that the input offset voltage is typically about 3 millivolts. Now, let's think about what we're doing here. We have about a 3 millivolt DC offset at the two inputs, and with a gain of 100, that's going to give us about a third of a volt DC offset at the output of this stage. Now, that in and of itself is not particularly bad in our application. Your ear is not going to hear a DC offset. However, it then goes to the second stage where we have another gain of maybe 30 or so, and all of a sudden that little DC offset becomes about 9 or 10 volts. Now, this first may cause problems if we feed this signal into other modules within our overall music synthesis system. And secondly, once that DC offset gets up to around 10 volts, it's going to begin clipping one side of the noise signal as it hits the saturation voltage. Now, you may say, well, it's just a noise signal. Why do I need to worry about a little bit of clipping? Well, although it is still a noise signal, it is not a white noise signal. I don't know what kind of noise it is, but it's no longer white noise, and it warps the character of that noise signal. You will be able to hear the difference if you start noticeably clipping one side of that white noise. Also, if the input offset voltage was higher than the typical value, or the transistor you were using was a particularly quiet one, it did not generate as much noise, so you had to increase the amplification, you might actually get the DC offset beyond the saturation voltage, and the second op amp becomes pinned at the power supply, and all you've got now is just a DC signal, and you can't hear that at all. One solution is to use the TL071 single op amp that has input offset adjustment pins. We can just hang a trimmer on those and trim out that little DC offset, and that would work. However, since we're building a device with several operational amplifiers in it, we may prefer to use the TL072 dual op amp or the TL074 quad op amp. Neither of these has the input offset adjustment pin, so we need to find another solution. We will actually implement a high-pass filter when we set up the gain of the first stage. This is done fairly simply by adding a capacitor in series with the resistor to ground from the inverting input. Now, what happens at very low frequencies, that capacitor just acts like an open circuit, and the op amp then just acts like a voltage follower. However, at higher frequencies, then of course that capacitor starts looking more and more like a short circuit, and the gain goes up to the nominal 101. The problem here is that we want a fairly low cutoff frequency to retain that low frequency information, as we mentioned earlier, but in order to keep the feedback resistor at a reasonable value, we've got to make that grounded resistor 100 times less than that, so it can't be too big, which means that in order to get a fairly low cutoff frequency, we've got to make that capacitor fairly large. Now, I have chosen 30K and 3 meg for the two resistors. That gives us a gain of 101, and a 4.7 microfarad capacitor. Now, those values, 30K and 4.7 micro, give us a cutoff frequency of about 1 hertz. Again, that's not really that critical. So that takes care of our first stage. The second stage, as I said, we want a variable gain between 5 and 50. So I have chosen as the feedback resistor to have a 100K in series with a 1 meg trimmer in order to adjust that gain. That's a total of 1.1 meg, and so to give us a maximum gain of 50, that means the input resistor should be 22K. And then, of course, we have our standard 1K output impedance, so we hang a 1K resistor on it, and there's our white noise. Now, there's one final little problem here, and that has to do with the fact that we are going to do some more processing on this signal to generate our other types of noise, and in some cases we're going to need a relatively high gain, and we'll see this in subsequent videos. However, remember the TL07X series has about a 3 millivolt input offset voltage, and so that's going to get amplified here. Now in this case, just for the white noise, if you get a few tenths of a volt DC offset, it probably does not matter as far as your white noise signal is concerned. Your ear won't detect that, and it probably won't generate any problems in other circuitry unless you've got a really big gain. However, since we will be feeding this into some filters with fairly high gain, we need to get rid of that little DC offset generated in this second stage. So we can simply hang a trimmer from plus 15 to minus 15 and the wiper through a 1 meg into the summing node of the op amp, and that will allow us to trim that DC offset out. It's actually easier to trim this once you have the subsequent circuits where it gets amplified some more and it's easier to see. Now, we'll talk about adjusting it when we talk more about the filtering later. In order to adjust this to give you your 5 volt signal out, this is a little bit tricky, because if you look at the typical noise signal, and this is the final output that I've shown here, where is 5 volts? Well, it's bouncing all over the place, so you just adjust that trimmer until you get close to peaks of about 5 volts. Now, as shown here, an occasional peak hits around 6 volts, but not too many peaks exceed about 5. You can argue a lot about whether you ought to try to reduce that so that none of the peaks go above 5 volts, but there's no way you're going to get an exact plus and minus 5 volt signal just due to the nature of noise itself. All right. In our next video, we will take this white noise signal and we will use that to generate pink noise, which is actually the hardest one.